Hey everyone, it's Dre here again, and we're going to be going through my first exam problem, which is dealing with scaling of a problem in order to use an ordinary differential equation solver in Python. So in our problem, we have a Stefan tube with a acetone and methanol liquid mixture at z equals 0, and at z equals delta, we have a screen with air blowing across it. And with this situation, we know that there is going to be that the mole fractions at z equals delta is going to be about 0, which is going to be important in the next part. But for now, we're looking at the acetone and methanol liquid interface, and we know that air is not going to be diffusing down into the liquid, so therefore we know throughout that the molar flux of component 3 in this case, which is air, is going to be equal to 0. So that's just a little bit of a background, but we also know all of the mole fractions of our acetone and methanol mixtures. We know the delta value, we know the pressure and temperature of the system, and we also know the Stefan-Maxwell diffusivity coefficients as well. So first what we want to do is we want to define the Stefan-Maxwell relationships, which we know is the change in the mole fraction of 1 with respect to z is equal to, wow, that is really shaky, hopefully it shows up all right, equals the mole fraction of 1 times the molar flux of 2 minus the mole fraction of 2 times the molar flux of 1 over the concentration times the Stefan-Maxwell diffusivity coefficient of 1 and 2 plus the mole fraction of 1 times the molar flux of 3 minus the mole fraction of 3 times the molar flux of 1 over the concentration times the Stefan-Maxwell diffusivity coefficient of 1 to 3. And we also know that the change of mole fraction 2 with respect to z is equal to the mole fraction of 2 times the molar flux of 1 minus the mole fraction of 1 times the molar flux of 2 over the concentration and the Stefan-Maxwell diffusivity coefficient of 1 to 2 plus the mole fraction of 2 times the molar flux of 3 minus the mole fraction of 3 times the molar flux of 2 over the concentration times the Stefan-Maxwell diffusivity coefficient of 2 to 3. And like I said before, this is going to go to 0 because the molar flux of 3 is equal to 0, so those are going to cancel out. That's going to be important for simplification going forward. So we have the initial conditions in the problem, so we can solve the initial value problem. But in order to use the ordinary differential equation solver in Python, we need some initial guesses. And we don't want to just pick any random number. We want to get a initial order of magnitude guess for this these molar flux. So we're looking for the order of magnitude of the molar flux of 1 and 2. And so what we want to do is we want to kind of use the scaling technique in order to get an initial order of magnitude guess for the molar fluxes of 1 and 2. So what I'm going to do is I'm going to define eta to equal the z over the delta. And what this is going to do is allow us to get a 0 to 1 scale because we know from z equals 0 to delta, we have essentially 0 to 1. And that's going to be important in order to allow us to solve the order of magnitude of the right-hand side of the equation a little bit easier. So you'll see this here now, where I'm going to define the change of mole fraction of 1 with respect to z, then goes to the change in the mole fraction of 1 with respect to eta times the derivative of eta over the derivative of z. And you can see this crosses out and that becomes the same thing as that. But regardless, what we're going to do is we know that the derivative of eta now with respect to z is equal to 1 over delta. times, and we want to keep this equal, so we want to times it by the change in mole fraction of 1 over the with respects to eta. So now, sorry, my fan blows my papers around sometimes. And now what we want to do is we want to plug this in to our Stefan-Maxwell equations that we came up with above. So now we have 1 over delta times the change in mole fraction of 1 with respects to, with respects to eta now, equal to the mole fraction of 1 times the molar flux of 2 minus the mole fraction of 2 times the molar flux of 1 over the concentration times the Stefan-Maxwell coefficient of 1 to 2. And then we're going to, like I said up here, this equals 0, so we can simplify this a little bit, and we have minus, and we know that the mole fractions all have to equal 1, so we can write that as 1 minus the mole fraction of 1 minus the mole fraction of 2 times the molar flux of 1 over the concentration times the Stefan-Maxwell diffusion constant of 1 to 3. So now we want to get a order of magnitude guess. And well, first let me simplify this a little bit further and multiply by delta, each side by delta. And so these are going to cross out, and we know now that we have a scale. Let me rewrite this so it looks a little cleaner. So now we know that the change of molar fraction of 1 with respects to eta is going to have to equal an order of magnitude of 1, because this can only go from 0 to 1 and this can only go from 0 to 1, so therefore that entire left side is going to be equal to 1. Now we want to make the right side of the equation also on an order of magnitude of 1, because they have to be equal on the left and right side of the equation. So we know that delta has to be from 0, or is on an order of magnitude of 1. We know that the mole fractions have to be an order of magnitude of 1, but we don't know the order of magnitude of the molar fluxes, and we can figure out the order of magnitude for the concentration and the diffusivity constant. So we know that by definition the concentration equals the moles over the volume, which equals the pressure over the ideal gas constant times temperature by the ideal gas law, and we're also going to multiply that by the Stefan-Maxwell coefficient. So we know from our initial values that the order of magnitude for pressure is 10 to the 5th, because we have it in kilopascals, but we want it in pascals, so you can figure that out yourself, but that's 10 to the 5th. And we know that the ideal gas constant is 8.314, but we're going to say that's about an order of magnitude of 10. And we know the temperature is 300 Kelvin, so an order of magnitude of 100, or 10 to the 2nd. And we also know that for gases, a rough estimate is 10 to the negative 5th meters squared per second. So now what we want to do, simplify this a little bit, so we know that these are going to cancel out, and we're left with 10 times 10 to the 2nd, or 1 over 10 to the 3rd, or 10 to the negative 3. So we have an order of magnitude for the denominator of this equation is about 10 to the negative 3rd. So we know that on the left side it has to equal 1, so we need our numerator to be the same. So we know that the molar fluxes then have a order of magnitude guess of 10 to the negative 3rd. And therefore we have 10 to the negative 3rd over 10 to the negative 3rd, that equals 1, and therefore we're good. So what we know now, okay, you can still see everything, is we know that our initial order of magnitude guess, which we're just going to use 10 to the negative 3rd as our guesses in the initial value problem for our Python solver. And so that will help us go on to the next part. Thank you.